Hello, everyone, and welcome back to the Computomics podcast. This is episode 3. Last week, we discussed our Pangenome browser and how we hope it can be used to visualize genomic changes in COVID-19. And as a general concept, we also discussed the need to plan ahead. And this concept to plan ahead, we also see emerge in the need to plan ahead for climate change within our food systems, and the obvious need for crops that can grow in different climates and different environments, or crops that are adapted to our future climates and our future environments, and the challenges that companies have with planning for those upcoming changes. This week, we wanted to discuss how big data can help companies and growers and breeders solve those challenges. So hi everyone, as I mentioned, we have Sebastian here with me. Sebastian, thank you for joining us again. And I know that climate change is something that we talk a lot about internally and something that we talk a lot about to our clients. And maybe you can start off with just giving us an introduction to the problem in your own words.
Sure. The climate is changing, as you rightly say, and it's something that we need to prepare for. Also in terms of the crops that we're growing. It means that some of the crops that we use today aren't going to grow anymore in the locations where we are growing them today. And for other crops, they might, maybe different varieties will be more adapted to the areas where we're growing them today. And that means that farmers need to switch to a different variety, for example. And there might be significantly better ones that maybe haven't been tried there yet that would thrive in these locations, and we don't yet have that knowledge, and maybe should be gathering it now so that we're prepared for these things. There is a long-term trial running in Austria where a lot of different corn varieties are being tested every year, different maturity groups. So farmers and growers and seed producers often distinguish different maturity groups. That means how long does the individual variety take from being sown to being harvested, so that it's ready for a harvest. And these different maturity groups mean that crops take a long time sometimes to mature, but then they have much higher yield. So you're trying to figure out into which maturity group does your crop fall, and where should you be marketing it. And essentially what this trial in Austria is uncovering is that there has been a shift almost every year towards the next maturity group that will have much higher yield. And essentially what you are growing in Austria today would have been grown in Italy, for example, a few years earlier, and what has grown well in Austria a few years earlier is now growing in Germany, or northern Germany even. And that means that there is a shift going on, and you need to figure out new and interesting varieties that could be grown in certain locations. And that means it's also possible to open up to new markets, so growers can actually start thinking about maybe buying something completely different than what they used to, because the climate in their area is simply changing in a way that makes it viable for other crops.
Right. So this essentially, as the climate changes, it becomes a predicting product placement dilemma, right? So if you understand the genetics of all your plants, and then you have to think about in what environment, in what climate would those genetics best be suited for. And if that is in fact the case, how can big data help with that question?
Exactly. Big data is actually required. The amount of data is quite large that is needed to have all of these examples and to understand what can be grown where. And we also need to react to the climate that is there in the first place to make, let's say, an educated guess of what could be grown there. But the variety or the number of things to try is still quite large, and therefore it does make sense to really try and see if we can predict some of these things, because the phenotypes that we are seeing and the effects that the climate has on the plant's performance is dependent on its genetics, on the information that it has in its genes, and the management of the field in which it's grown, and of course the climate and the soil in which it's growing. And all of this information together really makes the difference between a plant doing really well in a certain location and a plant really going to the bottom of its performance, or maybe even failing, which would be the worst possible outcome. So the information that a grower needs is, given the risk of maybe a more volatile climate, what's the safest bet that I can make in order to achieve as high yield as possible, but at the same time bringing up the bottom performance to a level where I still find it acceptable, where I'm sure that I'm going to at least achieve this amount of yield, for example. And in some cases, the European Union has been helping farmers, but in other parts of the world, you don't have these minimum payment agreements, for example, and farmers really only get paid for what they actually grow. And therefore, it's important for everyone in the world basically having information about what's the best variety to grow at this particular location. And if the things that I've been growing there for many years don't work anymore, what can I replace it with? There are different factors that go into that. There are established resources that can be used. And we think that we can add a lot of information by processing the historic data and processing all of the genetic information that we can get from the different varieties that are out there available commercially, and basically predict that for all of the farmers worldwide on every field worldwide.
Right. And to me, the logical question is, or the logical next step is, it seems like for that to really be at a prediction level that is worthy of being acted on and not just a hypothetical, let's say, research exercise, it's important not only to do the prediction, but to really break down the prediction into which portion of that performance is really due to climate impacts, genetic impacts, soil management, to really know that we are in fact predicting for future climate and not predicting based on something else, so that the prediction is an informed prediction. Does that make sense?
Yeah, it does. And the information that is needed is quite large, actually. So we do need to put together a lot of information from different sources. And especially this data integration is what teams have been struggling with. You often have a team that's made up out of breeders and quantitative geneticists, or people trained in statistics in general. And being able to build models that people can understand and that make sense to them is essentially what these teams have been doing, and they did as well as is possible with all of this information. And the next step, the next logical step in many industries has been that faced with such large amounts of data, you start using machine learning, because what you get with machine learning is the best possible model that approaches this particular data set, that approaches the outcomes of this data set. And that's what we are offering.
Right. And so that essentially goes to the question of, isn't this being done now, right? So when we look inside large breeding companies or even mid-sized breeding companies, we see computer science teams, data science teams, and there's also publications on using statistical approaches to correlate genetics, environment. Where is the room for improvement? So where's the advantage of machine learning?
So a big part of that really is the integration of different data sets all together and building a model that is able to capture the interrelations between the different types of data. So the genetics react to the environment that they find. And at the same time, the environment is often correlated. So things that you find in the soil have to do with maybe early frost or late frost, have to do with conditions on the water table, these kinds of things. And you have a very general overview with the statistical model, and you can also model individual pieces of that, but being able to integrate that is really difficult. And the thing that we are able to do is we can showcase these interrelationships, these dependencies on each other of these different variables. And machine learning is able to then approximate the best possible model that explains all of this data in ways that simply isn't possible for humans to put together such a model in the first place, because there are so many dependencies, and the amount of training that is needed for that, the amount of existing information is quite large, and especially in such very complex systems. So we're only now approaching the years in which this is even possible, because enough data has been collected. And then you need a team that is not only experienced in looking at different breeding programs, but also in applying machine learning in a way that can make sense of biological data. And most of the people trained in machine learning use image analysis or voice recognition as training examples, and they don't really look at biological data that much. So there's an opportunity for us to really be a team of scientists that know about different breeding mechanisms, different things about genetics, about bioinformatics, and about machine learning.
Right. And I think one thing that you really hit on, which I think is really important, is to make it useful, right? So to turn all of these conclusions, models, and predictions into something that can really be acted upon. So maybe on that note, can you give me an example of what a solution could look like from the machine learning perspective, but also from the breeder's perspective? So how does the data look like, and how does the data then look like to the breeder so he can make a decision on it?
Yeah, we are absolutely dependent on plant breeders working with us to establish these things for their crops. We aren't there yet in terms of plug-in models that completely replace the statistical approaches, or that completely replace what people have been doing in these departments for many years. We are simply there to provide an additional data integration solution for them that they can use and that they can benefit of the higher accuracy that it provides. And we really interact with breeders in the companies that we work with a lot about how to really use the data sets that they provide to us, how to really interpret the results that we get. And so we have 3 areas in which we are typically active. And these 3 areas are analyzing for which crops or climate or specific weather patterns the biggest impact comes from in terms of the prediction. That's something that is unique to our algorithms, actually, that we are able to showcase which areas of these data sets have the biggest impact for the prediction accuracy. And that's the information that we then report back, and that can help in, for example, planning ahead for a particular crop, or it can help also in selecting the kind of measurement that should be improved in accuracy. The data sets that we get often come from different sources, like Earth observation data from satellites, weather stations, in-field phenotyping, and finding out which of those are really the most valuable and the most impactful is an important part of what we can help do. The second thing that we can start with is really surveying the entire germplasm that's available for a breeding program, and just look at all the genetic diversity that's there for specific climate patterns that we maybe haven't even seen yet, that we maybe only anticipate, which of these pieces of the germplasm pool are the most relevant and could really bring the most impact to a new breeding program. If you're starting with new germplasm, if you're trying to get the crop adapted to a drier or hotter or wetter climate, then that's the kinds of questions that you can ask. And we are not limited to, let's say, replaying historical years in terms of weather. We can simulate different patterns. We can simulate different patterns of irrigation. We can also look at different management styles. All of these things that we've been using and where machine learning really shines is being able to generalize from existing data to a hypothetical new input and predicting from that. And then the third thing that we can do for our clients is really look at untested locations across the globe and see where these varieties that they've been developing and that they've been marketing could also be applied in other locations where they haven't been tested yet, simply given the soil conditions, the weather data, and so on.
Maybe a great way to wrap this up would be to give an example from real life in our collaboration with the International Rice Research Institute, IRRI, and how we've really taken a global breeding program and brought value to them with the kinds of predictions that we can make.
Yeah, so we've been working with the International Rice Research Institute on their rice breeding and line breeding and hybrid breeding. And something that they did was purchase different weather data from weather stations that had very accurate data sets. And they had up to the minute information about temperature, hourly information about precipitation, and so on. So it was quite detailed data. And the question was, if we have access to all of this information, and we have whole genome sequencing, which is also sort of the ultimate form of genotyping, the highest density, then does that really bring any additional benefit? Or would it be possible to, for example, use less genotyping information or use less weather data, maybe less dense weather data? And by modeling the accuracies that were achievable, we were able to show that really the temperature, for example, having a measurement of the highest and lowest points per day are actually quite sufficient to make the same kind of accurate predictions, because rice as a crop is well documented and well known to be reacting to the low nighttime temperatures. That's the kind of thing that makes a difference in yield afterwards, and that's what we also observed. And then we reported back. You could actually be using a lot less dense weather data. You could save money on gathering that information, and it would be enough to only have these pieces of information. So that's how we can then report back to breeders to say, the information that you've been gathering, much of it is very valuable. Some of it is actually in a level of detail that the models currently aren't able to use. We never know if that's going to change in the future. There's, of course, possibilities to have more accurate models that would then be able to use that information. But for now, the data that we have about all of the rest of the environment in which rice is being grown, the additional information from knowing exactly when the precipitation fell didn't actually improve the prediction, and therefore it's enough to simply have these more coarser weather data.
Great. Sounds good. Thanks so much, Sebastian.
Thank you.
Bye.
Bye.
So thanks everyone for joining us on our third episode, and I look forward to bringing you more value and discussing more relevant topics. Some things that we have lined up is to talk about pandemics within our food system, to talk about machine learning, metagenomics, and some other really interesting topics. So I hope you stay tuned. And as always, visit our website, computomics.com. subscribe to our podcast, leave us a message, visit our blog, and please connect with us on Twitter. Thanks so much. Bye.